Okay, folks, let's close out our discussion of the different rock types by discussing metamorphic rocks. So as you look at this particular rock here, you see a couple of different things. First, you see that it's broken up into light layers and dark layers, and that you have alternating bands of layers of different sizes. And secondly, you see that those layers are kind of all folded up in different spots. Like it's really squidgy looking over here, and it's folded, still a thick band, and it's folded a little less there, but it still seems like it's been deformed in some way. It's been, something about those layers has been squished. We know from our discussion of the rock cycle that metamorphic rocks are those formed by heat and pressure without melting. So these layers in this metamorphic rock here called gneiss, they never melted to form these textures. Instead, what happened was some amount of pressure, some amount of heat applied to the solid rock that this started as, caused all of this deformation to happen. So we will discuss a little bit more about the details as we go on. But when you see a rock like this, you should think deformation. Something has deformed or changed the shape of the rock. Some forces have deformed it. We'll talk both about the metamorphic rocks and about the process of deformation today. So our sub-lectures for this topic, first we will get into the metamorphism causes of metamorphism, and this concept of the geothermal gradient, which describes the rate at which temperature changes as you go down inside Earth. So as you go deeper, it gets hotter. And we can measure the rate at which it gets hotter, and we can then describe why it is that Earth is hotter when you go deeper. Later, we'll get on and talk about metamorphic composition and texture. Once again, those words will come up, those variables that we use to describe rocks. And in this case, we will have different composition and texture words to use for metamorphic rocks related to things like metamorphic grade and foliation. Then we will get into different types of metamorphism, which can happen at different spots on Earth's surface related to plate tectonics. And that will lead us nicely into our discussion of plate tectonics that is coming up. And then we will also talk about the processes of deformation in general and how faulting and folding are just sort of two sides of the same types of deformation events. So to remind you, metamorphism is caused mainly by heat and pressure. So increased temperature, increased pressure. Pressure is just, to put a different way, pressure, if you know from physics, is force exerted over an area. So you can really think of pressure as a type of force, although we're describing it over the entire area that it's pressed. And pressure can result from all sorts of different forces, but the main ones that we will think about are the force of gravity acting on rocks above rocks is going to push on them, and also the forces of plate tectonics of plates on Earth's surface pushing together is also going to exert a sort of directed pressure on those rocks. Another thing that we haven't brought up yet, but that does cause some metamorphism, is hot fluids, so water-based fluids, but they have to be hot and they contain other chemicals. So the chemicals in those hot fluids can sometimes interact with the rocks that are already there. They will leave behind some minerals, they will dissolve other minerals, but they have never melted. The rocks themselves don't melt if we're talking about metamorphism still. Once we start to get melting, we're really describing an igneous rock. So where would you have heat and pressure and maybe some hot fluids without melting? Well, it's not going to happen right at Earth's surface most of the time because the pressure isn't high enough here. There isn't enough heat here generally. So instead, you're looking at sort of moderate depths in Earth's crust. Sort of middle way down. As you go down a certain distance in Earth's crust, you will get to a point eventually at which metamorphism is happening. And as I've said already in this lecture, temperature increases with depth, but pressure also increases with depth. So as we go deeper and deeper, we will get to both higher temperatures and pressures. So we will get to higher grades of metamorphism. This geothermal gradient, here's a good definition of it, It's the rate at which temperature increases with depth. Since we're talking about rates, and this is an important concept throughout science to understand, this means one thing changing as another thing changes, right? If we are talking about the rate at which your car moves, we can describe a velocity, miles per hour. So distance changing as time changes. In this case, we're not talking about a time rate. We're talking about a temperature change as depth changes. So we can measure temperature in degrees Celsius, say, is what we'll usually use in geology. And depth, we're talking about large depths here, so usually we'll use kilometers. So when we talk about a geothermal gradient, look for some number of degrees per kilometer, and that represents a rate at which temperature changes. As you go down 1 kilometer, temperature will increase by X degrees Celsius. If you go down 2 kilometers, then temperature would increase by 2 times X degrees Celsius. We'll get into a little bit of math in this section, but it's not too bad. Just bear with me here. Occasionally, these high heat and pressure can occur near Earth's surface too, but the conditions are fairly rare for those. And we'll point those out when we talk about those different types of metamorphism a little later. So the geothermal gradient, and here is sort of a graph of how that geothermal gradient changes. If you're looking at this graph, the geothermal gradient itself would be represented by the slope of the graph. But if we just want to think about how the temperature changes, here we see, okay, so this is depth in kilometers, and this is temperature. And this is in Kelvin, but that equals degrees Celsius, just with a correction. So 1900 Kelvin is going to be 1900 minus 273 degrees Celsius. 3000 Kelvin would be the same as 3000 minus 273 degrees Celsius. So when you're looking at these numbers that are in Kelvin, it's pretty similar to degrees Celsius. It's just that you have to correct by that number there. I'm not going to have you remember that, although you may have seen that number already if you took like chemistry way back when. Just know that that's what Kelvin degrees are. They're like Celsius, only modified just a little bit. We don't need to talk about why. If we look at how Earth's temperature changes as we start at Earth's surface, it starts out pretty cold, and then temperature rapidly increases through the lithosphere down to a depth of about 410 kilometers. And since we're thinking about metamorphic rocks, this is really the area we're going to be thinking about. Because if you go too much deeper, the types of rocks that we have at Earth's surface, especially if they have any water in them, are going to start to melt. So above this, you can have melting happening, or you'll have different rocks entirely. We can see that that gradient, the slope here is pretty steep. Temperature changes pretty rapidly with depth, especially in Earth's crust. But it does continue to increase to a temperature of about 7,000 Kelvin once we get all the way to the center of the Earth. And throughout the mantle, it's above 1900 Kelvin. And through the outer core, it's above 3000 Kelvin. These are really hot temperatures, a couple thousand degrees Celsius. Why is it that Earth's interior is so hot? Well, there are a couple of things that contribute heat to Earth's interior. One is sort of ancient heat that came from accretion of Earth. So we think Earth started out as a bunch of planetesimals, think like asteroids, that were surrounding the early sun. And as these asteroids ran into each other, they were attracted to each other by gravity, right? And when they hit, right, if you think about an asteroid hitting Earth, you probably think of, some fireball hitting Earth, and then everything is really hot and there's a big explosion. Well, why is it hot? Because you're turning the gravitational potential energy of these things being attracted to each other. They start out far apart, but gravity pulls them together and now they're moving. And once they hit each other, all that energy's been converted into kinetic energy. But once they hit that relative motion of one asteroid, one planetesimal relative to another one, that stops. But that energy has to go somewhere. And where it ends up going is into heat. So at the center there, we heat up everything once they collide. And really all that's happening is we're turning the energy of gravity into thermal energy or heat energy. And despite the fact that all of this happened 4 billion years ago, a lot of that energy is still sticking around, raising the temperature inside Earth. So part of Earth's interior heat comes from accretion. A lot of it today comes from radioactive decay. So we've already talked about isotopes and how some of those isotopes decay over time, how they're not stable, and that decay releases some energy. So some isotopes of elements like potassium and thorium and uranium inside Earth are constantly giving off radiation and constantly heating up the interior of Earth, just because those isotopes are unstable and they have very long half-lives. So over billions and billions of years, these are breaking down, releasing energy, and keeping Earth's interior hot. So that's our second one, radioactive decay. The third one is heat from crystallization. It turns out that turning from a liquid to a solid actually releases energy. So as the mantle, which may have at least used to be partially molten, it's not so molten now, remember that it's mostly solid. And as the inner core itself have solidified, that started out as a liquid as well. As that has gone on and converted from a liquid to a solid, we've released some more energy. So these are the three sources that we'll talk about in terms of why is Earth's interior hot. Probably the main one today is actually this one. That's the one that we think the most about and contributes the most heat today. And it's what keeps a lot of things going. So if we didn't have a liquid outer core, we wouldn't have a magnetic field. And if we didn't have enough heat so that the mantle could at least flow a little bit, then we couldn't have plate tectonics. So the fact that Earth's interior is still hot matters a lot to us on Earth today. Okay, let's think about Earth's surface, and in some versions of this course, you may have had plate tectonics already, and in some versions, you're just starting to see a little bit about plate tectonics. What we have here is a block diagram showing a plate on Earth subducting under another plate. And at certain places along this plate, the plate is being pulled apart, and in some places, it's pretty calm and not much is going on. And so we have different geothermal gradients in each of these spots, which we'll start to think about as we break this out into the diagram below. So in one of these subduction zones where one plate is subducting under another plate, you've got a heat source from some molten material, some magma that's rising from that subducting plate. That makes the area around here hot from magma. And that's going to mean that we have a relatively steep geothermal gradient. So if we look at, well, I'll break that out in a second, but the idea is that we have, it's pretty hot in these zones where we have subduction. In places where a plate is actually pulling apart, it's even hotter because that really hot mantle gets closer and closer to the surface. And in places where the continental lithosphere, the stuff that the plates are made out of, is relatively stable and it's not pushing together and it's not pulling apart, then it tends to be a little bit cooler than those other spots. And we can, one way to measure it is the geothermal gradient, but another way to describe the heat within Earth is to look at the depth at which metamorphism stops and sort of melting and igneous processes really get going. So we can just denote that by sort of 1300 Celsius. If we take that as a ballpark figure, if you take any rocks at Earth's surface and you were to bury them to a depth where you had a temperature of about 1300 Celsius, those rocks would probably start to melt. Why isn't the mantle melted then? Well, because the mantle is made out of slightly different material. It's even more mafic than most of the stuff we have on Earth's surface. But if you took the typical rocks that you have on Earth, 1300 Celsius is enough to probably melt most of them, even at the pressures that you have at these depths. So 1300 Celsius sort of tells you where metamorphism would stop and igneous processes would begin totally, even if you're totally dry rocks. So in this hot area where plates were subducting, we hit that 1300 Celsius at about 50 kilometers. In places where the plates are pulling apart, we hit it even shallower at like 30 to 40 kilometers. And in stable continental lithosphere, we don't hit it until we get to about 150 kilometers. Now, where is metamorphism going to happen? In these rocks, it's going to happen it starts somewhere below Earth's surface, right? Because right at Earth's surface, it's not hot enough. But all this area here is going to be metamorphism happening. Same thing over here, but it's probably even shallower that metamorphism starts just because there's so much more heat at these spots. And a similar thing here, metamorphism. So, as I pointed out, this line here at 1300 Celsius shows you the depth above which metamorphism occurs, or at least can occur. And below this, most rocks at Earth's surface will melt. So if you missed that from the first part, think of that as being what these white lines here represent. Now we can bring in this idea of the geothermal gradient. So if you measure this out and you say, okay, this has gone up about 1300 degrees over 50 kilometers, and you do that math, this will start to look like a geothermal gradient. And we can just do this division, 1300 over 50, right? You can all do that in your head, right? It's 26. I don't actually mean that you should be able to do that in your head. That's 26 Celsius per kilometer. So, right, I've rounded it here to 25 Celsius per kilometer. But that's sort of a typical geothermal gradient that you would find in a subduction zone. About 25 Celsius you increase for every kilometer you go down. So if you start, what's our Earth's surface at? 15, 25 Celsius. So if you start at 25, then 1 kilometer down, it's going to be 50. And then another kilometer down, it's going to be 75. Until you go all the way down, you'll hit 1300 Celsius at about 50 kilometers depth. If we were to do that same math over here, we'd get about 40 Celsius per kilometer, where plates are extending apart, where plates are pulling, and that mantle is getting closer to Earth's surface. Whereas in a place where we don't have a ton of tectonic activity going on, so the lithosphere is pretty stable, it's ancient, it's cooled off some, then our gradient's more like 10 Celsius per kilometer. And this is the typical range. Somewhere between 10 to 40 Celsius per kilometer are pretty typical ranges for that geothermal gradient. So we've looked at where metamorphism stops on the deeper side, because rocks will probably start to melt. But we can also think about roughly where it begins in terms of the temperature, based on how much heat you need to start the very beginning of metamorphism. So these metamorphic reactions, changing one mineral into another mineral in the solid state without melting, that can start around 150 to 200 Celsius. If your temperatures are less than that, you won't have metamorphism. You don't have enough heat. Temperatures higher than that, as long as you're not melting the rock, you have metamorphism. It also turns out that's roughly the temperature which starts to destroy oil, coal, and even natural gas in rocks. So once you get into metamorphic rocks, you don't have those resources anymore. Just want to point that out. That'll come up later. Now we can use this idea of the geothermal gradient to start to think about more complicated geological questions. So Tennessee, about how deep under Tennessee are the rocks that are just barely being metamorphosed? Well, if we want to think about that, we have to know what's going on tectonically in Tennessee right now. We don't see a lot of volcanoes in Tennessee, any at the moment. We are really far away from any sort of plate boundary. The mountains that are nearby are very old. They're not lifting. There's no pulling apart. So this is much more like what Tennessee is. We're sort of in a region of very ancient, stable continental lithosphere. So if we want to know how deep those rocks are that are just barely being metamorphosed, we can use a geothermal gradient of 10 Celsius per kilometers. And we're trying to get to, our endpoint is 150 to 200 Celsius, somewhere in that range. What is our start? Well, depends on where exactly you look, but it's probably somewhere in the 10 to 20 to Celsius range for the average temperature across Tennessee. So 20 Celsius is 68 Fahrenheit. sort of average, if you average summer and winter together, maybe you get that number, right? We're just doing a ballpark number here, so we're just going to use 20 Celsius. And we say, in order to get from the start to the end, from 20 Celsius to 150 Celsius, how many of these kilometers do we need? If they're changing by 10 Celsius per kilometer. Well, okay, if we want to go to here, then that's 130 to 180, right, Celsius that we need to increase. So if we do the math for 10 Celsius per kilometer, and we've got 130 Celsius is what we want to get to, then how many of these do we need to get to there? We need 13 total. Or on the high side, we would need about 18 total. So under Tennessee right now, we would have rocks that are barely starting to be metamorphosed if we go down somewhere in the 13 to 18 kilometers range. You drill down 10 kilometers, those rocks probably aren't being metamorphosed too much right now. If you go 20, those rocks will be metamorphosed. If you go 30, they'll be metamorphosed. If you were able to somehow drill 150 kilometers below you in Tennessee, you would probably not be metamorphosing anymore. You'd probably be melting any rocks that are present. If that seems sort of weird how I did this math right here, let me give you a different way to do it. But we're still going to start with the same thing. So we're going to start at 20 Celsius, and that's at a depth of 0 kilometers. And our target is still 150 to 200. Let's just pick 150 to start. We're going to increase our depth by 1 kilometer, and then we're going to increase our temperature by 10 Celsius, because that's what our geothermal gradient says to do. And we're going to do it in just sort of a diagram here. So let's say 1 kilometer. How hot is it going to be? It's going to be 30 Celsius, right? We've just added 10. 2 kilometers, 40 Celsius. 3 kilometers, 50 Celsius. 4, 5, 6, 7, 8, 9, 10, going all the way. If you were to do this out yourself, you could convince yourself, okay, we go to 60, 70, 80, 90, 100 Celsius, 110, 120 Celsius, 11, 12, 13 kilometers, 130, 140, 150 Celsius. Just doing that same math that we did before, but with a diagram instead of sort of doing it in our heads with just a little bit of algebra-like stuff. We could also ask this question. When Pangea formed, it just barely metamorphosed the rocks in our area. So oftentimes in Tennessee, you'll find some shale and you'll find a little bit of slate. And that slate is indicating that we just started to metamorphose some of those rocks. You might find a little bit of quartzite, just a tiny bit of marble in Tennessee as well. Those as well mean that we just started to metamorphose the rocks. And we'll talk about those rock types in a little bit. If we just barely started to metamorphose the rocks in our area when Pangea formed a few 100 million years ago, about how deep were they buried back then in order for that to happen? So when Pangea formed, we had one continent crashing into another one. So this might be a better model to use in that case. And in order to make the math easy, we'll say that we start out at 25 Celsius at Earth's surface. And so you can say, okay, 1 kilometer down, we're at 50. 2, we're at 75. 3 kilometers, we're at 100. 4 kilometers, we're at 125. 5 kilometers, we're at 150 Celsius. Maybe we can say then that when Pangea formed, the rocks in our area in Tennessee were probably about 5 kilometers underground at that point, give or take. At least those ones that were just barely metamorphosed. So what's happened since then? Well, those 5 kilometers of rock have probably been eroded away since then.